Alright, good morning. Here we are again for another lovely session of MENG 3310 Fluid Mechanics. This is the 27th lecture in the video series, and today we're simply continuing on with some more examples of similitude, dimensionless numbers, and dimensional analysis. Alright, so let us begin. So all we're doing today is working through a few examples. Simple lecture for a Friday. Alright, so here. If I can manage to get my right color here. Example 1. Alright, so we are going to have this given. We are going to be looking at a scale model of a torpedo. Given. We want to study the drag characteristics of a torpedo using a water tunnel 1/5 scale model. Using a water tunnel 1/5 scale model. One-fifth scale model. And let's compare the model to the prototype. Model to the prototype. Again, the model is the scale model, and the prototype is the actual full-size item. So let's compare these two systems. The model will be using fresh water at 20 degrees Celsius. So our wave tank, or whatever it might be, will have fresh water at 20 degrees Celsius, and our prototype, the real torpedo, would have seawater at 5.6 degrees Celsius. At 5.6 degrees Celsius. And then we'll have the two different viscosities of the water. This will be important. Let us say that this should be Vm. And then looking these up in a table, I can find that the viscosities for each of these will be 1.004 times 10 to the negative 6 meters squared per second. And then for the prototype, it will be we'll have a viscosity nu p of 1.17 times 10 to the negative 6 times 10 to the negative 6 meters squared per second. Meters squared per second. And I am told also that the prototype will be traveling at, so Vp, the velocity of the prototype, this thing will be traveling at 30 meters per second. And that the length of the prototype, the length of the real torpedo, will be 5 times, well, this just comes from the scale model. It's 5 times the length of the model, whatever that may be. And of course, we know Lm is just equal to Lm. And we are told find the velocity of the model, Vm, given Reynolds similitude. Using Reynolds similitude. Okay, so our Reynolds number, so that's our task, and I think I'll work on it on the next page. So again, we're going to use the Reynolds number similitude, and we're just going to relate one quantity to another, looking at scales, looking at balance of different factors, and saying these must have a similitude about the Reynolds number. So the Reynolds number equation, which we'll see more of in later weeks, is going to be VL over nu. VL over nu. And when I say that this has Reynolds number similitude, what I mean is that the Reynolds number of the model is equal to the Reynolds number of the prototype. So they may have different lengths and different velocities and different viscosities in the fluid they're in, but these will cancel out with respect to the Reynolds number. So I would then have, if I substitute the Reynolds number equation in, I would have VL over nu for the model must be equal to VL over nu for the prototype. For the prototype. And this will then reduce to, if I solve for Vm, I get that Vm is equal to nu m V, okay, let's see, nu m Vp LP over Lm nu P. So just solving this one for Vm. So, oh wait, that should say, sorry, this is, yeah, no, that's right. Oh no, wait, no, something, sorry, that's, helps if I don't screw things up, sorry. Nu m Vp LP, managing to confuse myself. So, again, Vm equals Vp LP, and then nu m divided by then nu P over Lm. There, that should do it. Okay, so then we're going to have, now it's simply a matter of substitution. 1.004 times 10 to the negative 6 meters squared per second times 30 meters per second times 5 times Lm. So I don't know the exact length of either of these things, but the fact that I know the ratios is good enough. And then I'll have Lm down here, because LP is just 5 Lm, and then times 1.17, the viscosity of the seawater, 1.17 times 10 to the negative 6 meters squared per second. And this will come Vm to 129 meters per second. Anyone see a practical difficulty with this?
That's a really long distance.
Well, well, not distance. It's a very high velocity.
Yeah.
129 meters per second. What's that in miles per hour? Let's see. What's that in miles? That's the problem. I always think in miles per hour. Let's see. We can do that really quickly. Can someone convert that really quickly?
Yeah. Long distance inversion time, really fast velocity.
I always think better in English than metric, but still 129 meters per second. That's quite fast for any kind of, especially for any kind of contained system. A wind tunnel, it could be done, but for a water tank, that's actually quite fast. Let's see. Well, let's find out. I'm curious. Let's 288 miles per hour. Is that what you got too? Okay, yeah, so 288 miles per hour. That is, for a water tank, that is quite fast. You might be able to get a wind tunnel that could go that fast, but for a water tank, that is actually very, very fast indeed. So, that might be another issue to look at. So if you found that you couldn't actually make your, so this kind of illustrates the downsides with this, or the downsides with experimental models. When you use whenever you use a scale model, you're going to have to adjust something else. If you find that Reynolds number is the key to predicting behavior of your type of object and your type of system, well, if you shrink down your scale model to say, it's sort of a thing of trade-offs. If you shrink down your scale model to make it easier to build and operate with, maybe if the torpedo is 2 meters long, and instead of a 2 meter long torpedo, you use a 0.4 meter long torpedo. Well, that's easier to build. It's easier to move around. It's maybe something you can, if it's just a simple empty metal can or something, it's something you can build using just plastic or sheet metal, rather than something that you need to use a small lifting apparatus to move around. You can move it by hand. Smaller things are intrinsically easier to work with, but in turn you'll now find that the velocity of your fluid may become prohibitively large. As we said, that 288 miles per hour, that's a bit ridiculous for water flow. There might be some water tunnels that could go that fast, but I'd be skeptical, especially because the flow will go all kinds of turbulent. But maybe there's some application that I haven't heard of before. So it's one of those things that you really have to. It's one of those things you really have to carefully consider the benefits and drawbacks of. So anyway, let's look at another example. Another example. Okay. Now, I want to model the flow in a pipe. In particular, the pressure drop. However, the fluid I wish to model is very toxic. The fluid is highly toxic. Maybe it's carcinogenic. Maybe it's just maybe it has some biological contaminants in it. Maybe it's for lack of a better word, just imagine a giant cartoonish vat of green glowing slime. That's something a Captain Planet villain would have, where they pollute for the sake of pollution. You know, profits may be down, but pollution is up, so it's good. But anyway, so that is why I want to create a model in this case. I don't want to actually, in my lab, I don't want to actually bring this sort of toxic green glowing goo into my lab. So instead, I want to find a comparable system that I can use. And I don't have to bring this, I don't have to let the Captain Planet villain near my lab, except for the funding. I'll take that, though. Anyway, so it's highly toxic. In particular, we're interested in the pressure drop per unit length. Or in particular, we're just interested in the pressure drop. We are interested in I am interested in the pressure drop. Interested in the pressure drop. Okay, so let me draw out each of these. I'm going to have my prototype and my model. And this is actually going to be a 1-to-1 scale. They're going to be the exact same scale. And so it's going to be 1-to-1 scale. They're both pipes of the same type and the same diameter. The difference between them is the fluid. And so here, wow, I cannot draw this pipe today. It's clearly Friday. All right, and the diameters are both going to be 0.25 feet. Both 0.25 feet. .25 feet. All right. And so this will, I'll also label this as the prototype and the model. And the model. And the velocity here is 1 foot per second. And in the in this here, well, we'll see. Okay. Let's see. And we want to look at this here. Okay. Okay, So let's consider this. And the VM here is going to be unknown. The velocity for the model is going to be unknown. Okay, so let me compare the two fluids. This is going to be the toxic fluid. And it has a density, a rho, of 1.32 slugs per cubic feet. Slugs per cubic feet, and a viscosity of 6.5 times 10 to the negative 6 pounds second per feet squared. So viscosity higher than water. And then the model fluid will just be ordinary water with a rho density of 1.94 slugs per cubic feet. Slugs per cubic feet with a mu of 2.34 times 10 to the negative 6 pounds seconds per foot squared. And I am told also that for the model, we'll be using a delta P of 0.54 pounds per square foot, or 0.45 pounds per square foot. Okay? And I want to find delta P for the real system. So I know in my model that I have a unknown velocity. For whatever reason, I don't know the velocity in my model, but I do know the pressure drop in the model. I do actually know the pressure drop in the model, so that will be useful. And then I wish to go and find all of these other quantities. Or I wish to go and find the velocity in the model and delta P for the real system. Okay. So let's see. Solution here. Well, we're going to need some dimensionless numbers to describe the system. And let us say that we do need some dimensionless numbers to describe system. Working through the pi terms, I find that some ones we might use are delta P over rho v squared equals a function of epsilon over d, where epsilon would be the relative roughness, and rho vd over mu. And we'll see this one. We'll see this one later, but we're not going to be working with that one much today. Rho vd over mu. And so we could use something like this, or we might also say we want delta p. So let's use similitude. Use similitude, want delta p. And I know that I want delta P of the model to be equal to delta P of my prototype. Okay. Oh, not delta P, sorry. I want my delta P factor of my model to be equal to that of my prototype, because that's what I'm interested in. So we're not going to be working with this whole thing here. I'll be working with some of it, but okay, we'll see. So, oh, which one here? Which? This one? This is a row. Yes, sorry. Rho. It's clearly different. So this will be delta P. See, look, we have P, rho, and P. They're clearly different. They're clearly very different. Like a thing alike. delta P over rho V squared for my model is going to be equal to delta P over rho V squared for my prototype. So I want my two delta P terms to be the same, because if I'm interested in delta P, I want them to be the same. I want my two delta P terms to have similitude, I should say, in terms of their dimensionless number. And so if I solve for delta P, I will get the delta P is equal to delta P of, if I solve for delta P of the prototype, I get the delta P of, that is delta P of the model, times rho P VP squared divided by rho M VM squared. So it's going to be the change in pressure of the model, the pressure drop on the model, times the density of the fluid in the prototype, the actual toxic fluid, times velocity squared, divided by the density of the model fluid or water, and multiplied by the velocity of the model squared. So this is then 0.45 pounds per square foot times 1.32 slugs per cubic foot per foot cubed times 1 foot per second squared divided by 1.94 slugs per cubic feet VM times VM squared. We don't actually know the velocity in the model yet, though, either. Times 1.94 slugs per cubic feet times VM quantity squared. Okay. And so, what else do we got here? So these alone will not give us what we need to, this alone will not give me anything. But I'll be able to use this with another thing to then get my delta P. So I have that delta P equals some number divided by VM squared, essentially. Now I need to get the VM. And to get VM, I will say that the model must have similitude with rho VD over mu. Now, the reason I'm choosing these is because I found that my system used these three pi variables, or these three pi terms. This one here, epsilon over d, that's surface roughness over diameter. Regardless of whether it's the model or the prototype, those are going to be the same. Surface roughness depends on the material and its finish, so it's like like cast iron would have a higher relative roughness than polished stainless steel. It's a surface property. And D is the diameter, they have the same diameter. So that's why I'm not worrying about this particular one for this particular system. They're going to have the same epsilon over D. What I do need to make sure is that they have the same similitude about their other pi terms. And so I will then say rho VD over mu for our model is going to be equal to rho VD over mu for our prototype. And if I solve this for VM, I will get that this is equal to VP rho P, VP rho P, VP rho P dP mu M divided by rho M times dm times mu p. And the two diameters, the dp and the dm, are the same, so they're just going to cancel out. And then this will allow me to directly calculate my velocity for the model, my vm. And this will equal 1 foot per second squared, 1 foot per second, times 1.32 times 2.34 times 10 to the negative 6 divided by 1.94 times 6.5 times 10 to the negative 6, and this will equal 2.45 feet per second. Then if I take this VM and substitute it into the previous expression I'll get that delta P for the prototype is going to be 0.0510 pounds per square foot. 0.0510 pounds per square foot. And the takeaway for this, the moral of this, you might say, is simple. It is that, notice, sometimes we need multiple pi terms to achieve our similitude. We need multiple pi terms or resolve similitude about multiple pi terms. Sometimes we need to resolve similitude about multiple pi terms. All right, let's see. Let's see. I might have a little bit else. Let me think here. Okay. Yeah, I think that'll do it for today. I think we may continue on finishing up a little bit of that next time, but I think that will do it for today. I think on Monday we may discuss the limitations of some of this pi term and similitude analysis before continuing on to some other topics of discussion. All right, that'll do it. Have a good weekend, and as always, thank you.